0. So I want to find like the poles and zeros of this transfer function. So the poles either going to be the value of omega that makes this one 0 or this one 0. So 1 plus j omega equal to 0. That means that j omega is equal to -1. That basically means omega is equal to j times 1, right? So because if I multiply this by j, then it's gonna be, am I right? Yes. Yes, I'm right. Yeah, sorry. Yeah, so this is gonna be omega is equal to j1, right? So in this plane that we have real and imaginary, it means that the omega, it's gonna be right here. Omega equal to 1, it's gonna make this transfer function equal to the denominator of the transfer function equal to 0. So the first pole that we have, it's the first frequency. We don't do the j, right? But just keep this in mind that when we do in this plane, all the frequencies are going to be in the imaginary plane. That's why like the j is from. But here we know that the first frequency that causes this transfer function to have a pole is omega equal to 1. The next one, it's going to be j omega equal to -100. And again, if you just basically ignore the j, you realize that this is going to be at omega equal to 100. Okay, some people, they write this like 1 plus j omega over 100, right? So like it's going to be the same thing. So you just like have to make it equal to 0 and realize like at what frequency this would be 0. Okay, and for the zeros we have, can you guess what the 0 is? Yeah, it's going to be omega equal to 10. So this transfer function have 2 poles and 1 0. Now I want to know what kind of frequency response this transfer function causes. I want to know if it's a high pass filter, low pass filter, all pass filter, what kind of filter it is, and what are the cutoff frequencies, at what point it starts attenuating the input, right? So the solution to this, to basically get this understanding of how this transfer function behaves, is something called Bode plot, right? So Bode is the name of the person who invented this, but so Bode plot has 2 components. The first one, it's the magnitude, which I'm gonna go with the first magnitude and then I'll do the phase, but the first one is magnitude. Okay, so there are 2 things that I have to mention about this plot. So the first thing we're gonna do is the magnitude, and again 2 things I want to mention. The first one is that we do this plot in the semi-log scale. What does semi-log means? Means that we only have one of the, actually the other one is also like log in the log scale, but it's gonna be I'm gonna get to this later, but let's just like go with this one, that the frequency, it's gonna be in the logarithmic scale, not linear scale. One reason because of that is because like if I do linear 1, 2, 3, let's say like I want to show frequencies from 1 to 1 million, right? So then like if I have a linear scale, like I have to draw a very long axis. But if I do logarithmic scale, then what we need to do is basically we have, this is frequency 0, and then let's say this is 1, this is 10, this is 100, 1000, 10,000, 100,000, and finally 1 million, right? So we can fit it here. Also, something that you have to notice that unlike a linear scale that like we always start from 1, this is not the case for logarithmic scale. If you want to see, for example, what happens at the smaller frequencies than 1, right? Because let's say you want to know the behavior of this transfer function at very small frequencies, then in that case you can start this from 0.01, 0.1, 1, 10, 100, 1000, and so on. Okay, so this part, it basically depends on the problem and how you wanna where you wanna focus on. Each of these is called a decade. This is 1 decade, 2 decades, 3 decades, right? What are these? These are powers of 10, right? This is 10 to power negative 2. This is 10 to power negative 1. This is 10 to power 0, 10 to power 1, 10 to power 2, 10 to power 3. So this, each section is called a decade. Okay? So this is about the horizontal axis. The other reason that we do this logarithmically is because it's gonna be easier to cascade transfer functions, and I'm gonna talk about that later. So this is actually for the vertical axis. For the vertical axis, we are gonna have the vertical axis based on 20 log of the magnitude of hj omega, right? So this is actually also like logarithmic, but this is what we call decibel. 20 log of something, we call it decibel. Okay, just keep that in mind that in mechanical applications or acoustic applications, they use 10 instead of 20, but we in electrical engineering, we use 20 because basically what this represents is power, and power is proportional to voltage squared, right? So even if you use 10, this would come out of the log and becomes 20. So that's why we use 20. And why do we use this one in logarithmic scale? It's mainly because, let's say if I have 2 transfer functions or 2 circuits and I cascade them. If I cascade them, their transfer function get multiplied by each other, right? But if I do this linearly, how can I multiply one plot by another plot? It's going to be very difficult, right? But if I do it in the log scale, log of